Thank you.
Two close-packed structures. Close-packed structures consist of close-packed layers of atoms within which each atom is surrounded by 6 others.
This is wild. This is just the last thing that would be cool to get, right? This is how you can layer hexagonal close pack structures. It's like if you had billiard balls all packed in on a table, they'll make these hexagonal structures. And then if you place balls at each threefold corner, then you'll get there's 2 different ways to do that, right? And that's where it's wild. Like, how could there be 2 ways? But just watch.
The difference between the two close-packed structures lies with the way in which these layers are stacked. In no case do 2 close-packed layers lie on top of one another. Instead, each atom sits in a dimple formed by 3 atoms in the previous layer. We will use color to represent the layers. Here, each blue atom sits in a dimple formed by 3 green atoms in the previous layer. Imagine that a second layer of green atoms is added so that it is equivalent to the first layer of green atoms. Then, a second layer of blue atoms is added that is equivalent to the first layer of blue atoms. This alternating layering of close-packed layers generates a structure that is known as the hexagonal close-packed structure. A second layering scheme is as follows. The first 2 layers are the same as before, with each blue atom sitting in a dimple formed by 3 green atoms. In this case, however, the third layer is applied in such a way that it is not equivalent to the first. If this stacking pattern is repeated, with every third layer the same, this generates a structure known as the cubic close-packed structure. The second packing pattern is called cubic for a reason. The structure is equivalent to the face-centered cube. Here we use color to illustrate the close-packed layers within a face-centered cubic cell. Let's take a moment to review. The unit cell for the simple cubic structure contains the equivalent of 1 atom inside the cell. The atoms touch along an edge of the cell and the coordination number is 6. The unit cell for the body-centered cubic structure contains the equivalent of 2 atoms inside the cell. The atoms touch along the cube diagonal of the cell and the coordination number is 8. The unit cell for the face-centered cubic structure contains the equivalent of 4 atoms inside the cell. The atoms touch along the side diagonal of the cell and the coordination number is 12. The hexagonal close-packed structure consists of close-packed layers of atoms stacked so that every other layer is identical. The cubic close-packed structure consists of close-packed layers of atoms stacked so that every third layer is identical. This structure is identical to the face-centered cube. It therefore has the same occupancy and coordination number.
But I didn't never notice that, but they don't explain what the coordination and occupancy of the the first hexagonal closed packed structure is. Did you guys catch that? There's like these last two.
The cubic close-packed structure consists of
There's this guy, which is FCC, right? But then this one is, what is this one? I guess that's HCP, hexagonal close packed. I thought this was a pretty cool video, though. I mean, this has been, it's probably one of the most widely viewed science videos out there. And it's 640,000 views. 640,000 people care about this stuff. Can you believe it? I love it. Let's see here. Let's try it. Let's see what this one is. Okay, come on. Now the structures part two. Let's look at this one.
So now we get to add electricity to our quiver of arrows, and this is where things get really interesting.
Okay.
the face-centered cubic lattice contains 8 atoms at the 8 corners of a cube and 6 additional atoms in the faces of the cube. Although the face-centered cubic lattice is often drawn to emphasize the cubic nature of the structure, it is also a close-packed structure. The face-centered cubic results from the stacking of close-packed layers in an ABC fashion, so that the fourth layer lies over the first layer, the fifth layer lies over the second layer, and so on. Here we use color to represent the 3 close-packed layers in the face-centered cubic lattice. Two types of spaces or holes exist between the layers of close-packed structures. The first type of hole is called an octahedral hole and is formed between 3 atoms in one close-packed layer and 3 atoms in a second close-packed layer immediately above or below the first. The space at the center of a face-centered cubic is actually an octahedral hole and is formed by 3 atoms in the green close-packed layer and 3 atoms in the blue close-packed layer. In all subsequent discussions, we will represent octahedral holes with partially transparent polyhedra as shown here. Despite the name, it takes 6 atoms, not 8, to define an octahedron. The term octahedron is derived from the fact that such a polyhedron has 8 sides. The center octahedral hole is the only one that lies entirely inside the cell shown here. Other octahedral holes lie partially inside this cell. The center octahedral hole shares each of its 12 edges with 12 other octahedral holes. 8 of these are shown here. Each of these lies 1/4 inside the cell. Overall, an array of n atoms in a close-packed structure actually gives rise to n octahedral holes. The second type of hole that exists between the layers of close-packed structures is called a tetrahedral hole. Tetrahedral holes are formed between 3 atoms in one close-packed layer and a single atom in a second close-packed layer immediately above or below the first. As before, we will switch to transparent polyhedra to represent the tetrahedral holes in our face-centered cubic lattice. The cell shown here contains 8 tetrahedral holes at the 8 corners of the cube, and these lie entirely inside the cell. An array of n atoms in a close-packed structure gives 2n tetrahedral holes.
Hmm.
Several different ionic lattices adopt structures in which one set of ions form a face-centered cubic array and the other set of ions occupies the octahedral or tetrahedral holes. In the following sections, we will discuss three ionic structures that can be described in this way. Halite is the mineral name for sodium chloride. In the halite structure, the relatively large chloride ions, represented by the green spheres, form a face-centered cubic array. The sodium ions, represented by the white spheres, occupy the octahedral holes. Each sodium ion lies at the center of an octahedron of chloride ions. Since an array of n close-packed atoms give n octahedral holes, and since there is one sodium ion for every one chloride ion, all of the octahedral holes are occupied. In contrast, the tetrahedral holes are vacant. We can gain a different perspective on this structure by examining a space-filling model. The structure is based on a face-centered cubic array of chloride ions and therefore contains close-packed layers of chloride ions. By removing successive layers, we see that the sodium ions as well as the chloride ions form close-packed layers. The structure can therefore be described as alternating close-packed layers of sodium and chloride ions. A second ionic structure that is based upon a face-centered cubic lattice is the fluoride structure. Fluoride is the mineral calcium fluoride. In the fluoride structure, the calcium ions, represented here by the white spheres, form a face-centered cubic array. The fluoride ions, represented by the green spheres, occupy the tetrahedral holes. Each fluoride ion lies at the center of a tetrahedron of calcium ions. Since an array of n close-packed ions gives 2n tetrahedral holes, and since there are 2 fluoride ions for every 1 calcium ion, all of the tetrahedral holes are filled. Last, let us examine a space-filling model of the fluoride structure. The space-filling model shows us that the array of calcium ions is greatly expanded to accommodate the fluoride ions. The primary reason for the adoption of this arrangement is stoichiometry. A third ionic structure based upon a face-centered cubic lattice is the sphalerite structure. Sphalerite is the cubic form of the mineral zinc sulfide. In the sphalerite structure, the relatively large sulfide ions, represented here by the yellow spheres, form a face-centered cubic array. The zinc ions occupy the tetrahedral holes. Each zinc ion lies at the center of a tetrahedron of sulfide ions. However, since an array of n close-packed ions gives 2n tetrahedral holes, and since there is one zinc ion for every sulfide ion, only half of the tetrahedral holes are filled. Last, let us examine a space-filling model of this structure. This model shows us that the sulfide ions are quite large in relation to the zinc ions. As a result, the zinc ions almost fit entirely inside of the tetrahedral holes, with only a small expansion of the sulfide lattice. Let's take a moment to review. The halite or sodium chloride structure can be viewed as a close-packed array of chloride ions with the sodium ions in all of the octahedral holes. The fluoride or calcium fluoride structure can be viewed as a close-packed array of calcium ions with the fluoride ions in all of the tetrahedral holes. Last, The sphalerite or zinc sulfide structure can be viewed as a cubic, close-packed array of sulfide ions with the zinc ions in half of the tetrahedral holes.
Okay. So, I have some chemistry questions here. And my first chemistry question is, why are the sodium ions smaller than the chloride ions?
Because they're cations and they lost an electron.
Yep. So, how does that one electron make such a large difference in the size?
Electron repulsion and shielding.
Okay. What?
Electron repulsion and shielding. By not having that one electron there,
Shielding?
you would make less of those things, which would make the ion smaller.
You'd make less of things. Okay. I'm sure you're right. I can't quite follow it. Who has a different explanation for that?
Would it be, I'm not sure if this is right, but would it be because it's in a new valence shell? Or is...
Mm-hmm. Yeah, I mean, so like sodium and chloride are in the same, like sodium is in group 2 or in row 2, right? So sodium and chlorine are in the same row. And, so chlorine has a ton more electrons, but the sodium is really contracted and the chlorine is rather large. And even like, chloride is larger than zinc, it's larger than a zinc ion. So I'm kind of going a little bit with Vigo here, even though I didn't quite follow his answer. Brian, do you have any thoughts on this, or?
Would it be because that one electron, it increases the effective nuclear charge or negative effective nuclear charge of the nucleus?
That's a really interesting concept. Yeah, right. So that sort of like goes along with Vigo's answer about screening, right? I think maybe not. What do you mean by screening, Vigo?
So, okay. When you have the electrons, right, they experience repulsion forces from one another because they're of
Yeah.
the same charge. So
Right.
when you have like electrons in the 1s, 2s, etc., you're going to have electron shielding from one another because they're going to be shielding the other electrons from the nucleus. So I'm saying that by taking away that one electron, you'd be not only decreasing electron repulsion because you'd have less electrons, but you'd also be decreasing the amount of electron shielding because that one electron isn't going to be blocked out by the electrons in the, what is it, 2p orbital? Since we're talking
That
about
makes
sodium.
sense. Yeah, actually, I get you now. I'm following you now. So one thing that Brian said was like he said the effective nuclear charge, right? And so I am not exactly sure how to define that, but it seems to me like the cations have a larger effective nuclear charge, right? Because for every electron you strip away, the nucleus exerts a stronger force on the residual electrons, right? On the remaining electrons. Doesn't that make sense, Vigo? Like if you had a neutral chlorine, yeah, go ahead.
Oh, I don't think that effective nuclear charge is based on the electrons. I think that it's based on the stuff that's actually in the nucleus. I think that the electron shielding and repulsion just affects the overall like radius and whatnot. But I think for effective nuclear
Mhm.
charge, that stuff is only based on what's in the nucleus.
Okay. Is that right, Brian? Or
I think so.
okay. So, but I mean, why do they call it effective nuclear charge instead of just nuclear charge then?
Because it's the force that the nucleus exerts to keep the electrons like where they are.
Hmm. Okay, that makes sense. So it sort of diminishes for every shell that's filled, right?
Yeah.
The effective nuclear charge that the valence electrons feel is less than what the inner electrons feel. Yeah.
Yeah.
Yeah. That's a cool one. Did you guys ever hear the story of Henry Moseley? Henry Moseley was he actually worked with Ernest Rutherford, and he was a bit of a racist. I mean, he was kind of a weird guy, but he was really bright apparently, and he was really doing kind of amazing things in the lab. And what Moseley discovered was that if you look at the um, energy of the X-rays produced by an atom, they increase with the square root of the nuclear charge, right? So, um, so like hydrogen, helium, lithium, beryllium, blah, 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 you go up to, get up to 92 or whatever you get uranium, right? And at that point, the the X-ray or the ultraviolet ray that's produced by the hydrogen atom is like the square root of 90 less energetic than the X-ray produced by the uranium nucleus. And that was an interesting result, I thought. Yeah. So yeah, he had a little bit of a sad life too, because he was in graduate school, and he got drafted into World War One, and he died in the Battle of Gallipoli in Turkey, which was just like um, it was like this horrible, just throw people into this valley and let them slaughter each other kind of madness that was going on at the time. But let's see. Uh, where's Moseley's? So yeah, he really that was important in sort of quantifying the atomic number, right? So as the the charge of the nucleus increases, the binding between the innermost electrons and the nucleus increases a lot too. And I actually had it wrong in my mind. I thought it would increase as the square of the number of electrons, but it's the square root. And let's see here. Yeah, let's look at Moseley's law here. Yeah, so copper, nickel, cobalt, iron, manganese, chromium, vanadium, calcium. As you go up in atomic number, the energy increases, you know, as the square root of that. or the square root of the energy. So V is proportional to Z squared. Oh, I was right originally. Okay. Sorry. So the energy is proportional to the square of Z. I'm sorry, I had that wrong. But and this is one way that they, there's a couple of cases, cobalt and nickel, for example, where cobalt weighs 59 roughly, and nickel weighs 58 on average. Now, these are the isotopic averages, but cobalt has a higher atomic number than nickel. Does it? No, it has a lower atomic number than nickel. And so people were a little bit confused as to how to order them on the periodic table. But Moseley sorted it out. He said, no, the nickel X-ray is more intense or more energetic than the cobalt X-ray. Therefore, it's should be at a higher atomic number. Hmm. It's all based on the Bohr model here. Put in a couple of quantum numbers, and you can get these energies to pop out. MQE squared, QZ squared. This is the one that's changing, right? As you change the atomic number, as you change the atomic, the charge on the nucleus, and that guy gets squared, then I'm not exactly sure how these N values fit in, because NF is going to be larger for the heavier nucleus, right? Because that's the, there could be like, principal quantum number 1 for the first row, 2 for the second row, 3 for the third row, 4 for the fourth row, etc. So not quite sure how that N squared and this Z squared interact, but anyway, so you can get to it that V is equal to this value times Z minus 1 quantity squared. Pretty cool. So, all right, let's ask another chemistry question here. Let's ask a real basic question. Why does sodium chloride dissolve? Oops, let's see if I can get this guy to focus there. Okay. And there's let's think about the factors. The energetic factors involved in the dissolution, and not entropy. Just the internal energy of the molecules. Okay. So let's okay. I'm going to let you guys choose your own breakout rooms. Okay. So let's go ahead and think about this question about why sodium chloride dissolves in water. Okay. So Brian, I'm going to assign you to room 6. Max, I'm going to assign you to room 8. Alicia, I'm going to assign you to room 2. And Kita, room 1. Lucas, room 8. Rachel, 5. Sadana, 9. Tavleen, 7. Vivian, 3. Rohan, 5. Jimin. Hey, buddy.
Can I ask you a quick question?
Sure, let me finish getting these students into their breakouts.
They're in the breakout right now.
Yeah, well, they're going there.
Okay.
I'm assigning
Sorry,
them.
I thought you were actually like giving grades or something.
No, these guys all get C's.
Oh, geez.
Yeah. Oops. All right. Oh, we're in a room together. Oops. No, we're not. Hey, guys. So what do we decide?
We said because the bonds break, but obviously that's
Well,
a
no,
pretty simple answer.
no, that's good. That's good. That's the first energetic contribution, right? It's bonds, right?
Mhm.
There's bonds between what and what?
Sodium and chlorine, or like
Na.
chloride, I guess.
Right. Yeah, exactly. Sodium chloride bonds, right? So what bonds form? Because the breaking of the bond is what we would describe as what, exo or endothermic?
Would it be exo because it's letting off heat,
What do you think, Sedona?
or would it be endo? I don't know.
I think it's exothermic. I'm not sure.
Okay.
I think
Well,
it is exo.
it depends on the bond, right? And it depends on what's forming afterwards. But if you just think about taking a sodium and a chloride and pulling them apart as sodium ion and chloride ion, then that is endothermic, right? Because you're having to tear the positive away from the negative. So you have to do work on the system. That's endothermic, yeah?
So it absorbs.
Yes.
Okay.
Yes. It does.
Okay.
It's one of the few reactions that, and there are other examples of dissolving salts that are like this, where when you dissolve it, the solution will cool down. And in that case, that is actually an entropy driven reaction, because that's where there's just so much there's so many possibilities once you put it in the water that it's like, oh wait, no, I lost you, you know, like, and it's like, oh, you know, and it's like the atoms are left with less energy internally than they had before, just because the other ones can get lost, you know, and they're like, oh, where are you? I can't find you, right? That's entropy. Yeah.
Hmm.
Yeah. Cool. All right. So NaCl bonds break. Now ask yourself, what bonds form? Okay.
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 We have a question.
Hmm.
Is ionic bonding an intermolecular force?
I don't know, are ions molecules?
Okay, so we're gonna look this up. I do not think it is.
I'm pretty sure I learned this in AP Chem. It is.
It's a bond type, not an intermolecular.
I learned it
force.
from the daily videos. Always trust the daily videos.
But it's a semantic question, right? It doesn't matter.
No, I think it does.
Okay, all right. But the thing is, like, what holds sodium chloride together?
And
Ionic bonds.
Ionic bonds, right? So you could say that it's electrostatics, right? It's just, you know, these monopoles, these electronic monopoles, they just stick together because when they're together, there's less total separation of plus and minus, right? If you're just like take the three cardinal axes, right, and just expand them such that the ions were pulled further apart, that would be, would that be exo or endothermic? So if you were to take the sodium chloride or, you know, unit cell or whatever, or a crystal of it, right, and you're to expand it, you're not changing the size of the atoms, you're just separating the atoms or the ions, right?
Mm-hmm.
Would that be exothermic or endothermic?
Endo?
Raymond?
The exothermic? I don't know. Let me.
Okay, explain it to Raymond. Right, before I get
I think
back.
I actually know the answer.
Yes. Okay. Explain, Fiona. Explain.
So breaking bonds is endothermic because you need energy to break the bonds.
Right. Basically, yeah. So, okay. Good. All right. So we've decided then, I think, that part of the dissolution of water is endothermic, right? So why does it happen? Think of the bonds that are formed. I have to leave the room. I have to leave the breakout room. Hello. Ah, did I put, oh, no,
Hello.
Caleb showed up. He showed up.
No, I'm here. It's just chilling.
But you were not, your camera was off. When it was
That's
just
true.
boring Roger. Oh my God. All right. So Chris,
Hi.
how's it going, buddy?
It's okay.
Alrighty. So if you take, Chris,
Mm-hmm.
a lattice of sodium and chloride, and you expand that lattice in 3 dimensions, in X, Y, and Z, right? Such that the atoms move apart from each other.
Mm-hmm.
Is that process exothermic or endothermic?
I think endothermic because the charges want to be close to each other. So you have to put energy in to expand it. My reasoning is like the positive and negative charges want to be with each other. Wait. Did you say sodium chloride?
Yeah. Mhm.
Yeah. So the NAs and the CLs like want to like be with each other. So then to break it apart, you have to put in energy. That's my
Right.
logic at least.
I like your logic.
Okay.
All right, Ankita. Do you get it?
Yeah.
Yeah, cool. Can you paraphrase it?
So he basically said that because NaCl, they're attracted to each other and they have opposite charges. So that if you want to kind of pull them out, that you need to put energy in order to expand that.
Exactly. Excellent. What grade do we give them, Caleb?
I would say
A, B,
A
C, D,
minus.
or F?
A minus.
A minus. Oh, I like it. I like it.
Pretty
You got
solid,
an A
pretty
minus. I don't know how you get an A, but okay. So if that's endothermic, then why does it dissolve?
We said that.
Don't answer that. Don't answer. Don't
right.
answer. I can't hear you answer. I cannot hear you answer. I can't hear you yet.
Okay.
I have to leave, and I'll come back, and you can tell the whole group. Okay.
Hello.
Hey guys.
Hi.
No cameras at all. Okay. All right. So, oh, there we go. Hello.
Hi.
Hi, Alicia.
I'm getting my windows clean behind me, and I feel like that would be pretty distracting.
That's totally fine. Totally fine. Totally fine. So, question for you guys. If you have a sodium chloride lattice, I'm trying to indicate with these 8 fingers, the positions of the 8 atoms in like a cell like that, right?
Yeah.
And then you expand them and you pull them apart. Is that exothermic or endothermic?
Just the process you described would be endothermic.
What do you think, Emma?
I was kind of thinking the same thing.
Mm-hmm. Why?
Well, I don't really know how to. One second. When it expands, it. If I could interrupt. If I could try.
Yeah, go ahead. What do you think? Shall we let her try?
Yeah.
Okay, go ahead, Alicia.
Atoms, they're bonded when they're a salt. So to separate the 2 atoms, you need energy. So which would make it endothermic because you have to put in energy to separate the 2.
Okay. What about in terms of, and this is all correct, right? But think about it in terms of the forces that you have to exert on the atoms, right? In other words, are the atoms going to do work on you? Are the atoms going to push apart, or will you have to pull them apart?
Well, the last time you asked this question, you kind of said it could be either. Depends on how you look at it. So I don't.
Oh shoot! That wasn't what I meant to say. I don't think.
Oh.
So wait a minute. Maybe let's clear this up. So if you just have 2 atoms, have a plus and a minus, right?
Yeah.
They're sitting in there kind of close to each other, sort of touching, right? And then you pull them apart. Well, in other words, will they be pushing apart or will you have to pull them apart?
You'll have to pull them apart. Yeah.
You gotta let Emma answer, Alicia. Oh. She's like, oh, it's like almost there, and then you're like, oh. Okay, so So if you have to pull them apart, is that exo or endothermic?
Well, endothermic is when it absorbs heat, right? So
Right.
yeah, the endothermic.
Yes. 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 Good. I didn't lead you on at all there, did I? Excellent. So for sodium chloride to dissolve, you have to separate the ions, right? So why does it dissolve?
Well.
Okay, don't answer.
Oh,
Don't answer.
Oh,
Don't
okay.
answer. Don't answer. You and Alicia have to come up with an answer, right? And I'll be back. I mean, we'll be back in the main room, okay? All right, I have to leave. I have to leave. I can't let you answer. Hey, guys. So, how are we
So-
doing with this?
I think we got it.
You do? Okay, tell me.
Okay, so when the salt crystal is submerged in water,
Yes.
The bond created between the water molecule and the sodium, so the ion dipole attraction is stronger than the attraction between the sodium and the chlorine attraction, the ionic bond. So I think that's why the sodium atom and the chlorine atom is separated.
Okay. All right. That sounds correct to me, but I'm not sure if I believe you. It's sort of like one of these completely unfair things that happens every day in courts of law, right? Someone goes and tells the God's honest truth, but nobody believes them. So I don't believe you. So, Vivian, what's wrong with this explanation?
I'm not sure.
Okay. All right. So Vivian, answer me this. I'm just joking around with you guys. But if you imagine these, I'm sorry, these fingers, right? These are the atoms in a sodium chloride lattice, right? They're all stuck together. And then because you can play God here, you just expand them out, right? Is that an exothermic or an endothermic process?
That would be endothermic since you're breaking bonds.
Wehan is saying something, but I can't hear him. So let me ask you, if you just have a plus and a minus, right? And they're stuck together, well, a plus and a minus, a cation and an anion, right? Just in the gas phase, will they stick together?
Wait, sorry, could you repeat that?
Yeah. If you have a cation and an anion, just in the gas phase, in a vacuum, right? Will they stick together?
No.
No?
I don't
Why
know.
not? Okay. Well, just on the basis of charge, right? If they're sitting there a few nanometers apart, will there be a force on the nuclei, or on the atoms rather? The positively charged atom and the negatively charged atom. A force of attraction or a force of repulsion?
Well, attraction?
Yep, exactly right. And they're going to get close until they start to touch. And then other repulsive forces will take over, right?
Mm-hmm.
And there are just many descriptions of those forces, but basically these guys will they'll be pulled together and then they'll touch, right? So if the atoms pull together and they touch, that's called an exothermic process, right? Because really what the atoms are going to do in order to touch is they're going to do work on the environment. Right? They're gonna be pushing. I mean, it doesn't work in a vacuum, right? In a vacuum, they'd have to emit that energy somehow, otherwise they would just bounce off, right? But if they're going to form a bond, they're going to do work on the environment, and that is called exothermic, right? Because when they form the bond, the environment gets hotter. Yeah, cool. So similarly, if you take them apart, you have to do work on them. You have to pull them apart, right? And that's referred to as endothermic because you're doing work on the system, right? The system is are the charges, right? Cool. All right. So from this perspective, sodium chloride dissolving is endothermic, right?
Right.
Okay. And Wehan said something about water. I don't even know. He's crazy. Just kidding. But anyways, so I think that's a good explanation. And I'll just push you to the next level and ask you what contribution entropy has in that process. Because you just described it perfectly from the energetics. Now the entropics are also important. And I'm gonna leave you guys now because I have to visit one more group and then we'll all join back in the main group. Hey guys.
Hi.
Hi.
Hi. So tell me, how many of you all have this strange impression of Rohan? Like right from the very beginning, because he's like appearing from this black void. I mean, everybody else is in a room with white walls or something, but in Rohan's case, it's this flickering darkness. It's wild. That's why I always go like Darth Vader. Can you do a Darth Vader for us, Rohan?
I cannot. I don't.
Oh, you almost have James Earl Jones's voice. You can't say, Luke, I am your father.
I'm gonna be quite honest. I never watched.
Oh, no kidding. Okay, all right. I'm just dating myself here. I'm just an old fart. I watched that in 1981, I think. I watched the original Star Trek. I know, it's crazy, yeah.
Before I was born.
Yeah, I know. But it was like yesterday for me, and I was with Christine White at the time, and I was so excited. But she didn't like me, but I was excited anyway. But but anyway, so on to sodium chloride. Did you guys figure this out, by the way? Do you know what the energetics of this process are and whatnot?
We know that it's
Or did you not?
by dipole,
yeah.
or it gets separated by the water, and then it stays separate by dipole moments, or what we think is dipole moments. But we don't really know what energetic forms were, other than entropy, which you said to exclude, and enthalpy, which was neutral, basically, because it takes energy to break the bond, and it releases energy when it forms a new bond, right?
I like it. So, do you think that you guys could create this so that Jimin could explain it to the whole group when we come back? I think she would do a wonderful job. What do you think, Hannah?
No, yeah, Jimin would definitely be the best candidate.
I think so. I think so. Okay,
Wait, and
cool. Rachel,
wait, enthalpy is
go ahead.
enthalpy is an energetic factor, right? That counts, right?
Right,
Enthalpy, like heat
right. Yeah,
exchange, that counts.
yeah.
Okay.
Yeah. Enthalpy is enthalpy, free energy, entropy. They're kind of bookkeeping, right? I hate to say this, but they all have mathematical reality, but the actual physical reality is a little slippery because they sort of partition between, pressure, volume, and internal energy, and enthalpy or entropy and other things. So they're a little bit hard to pin down from a physical perspective, but they are the way to keep track of energy.
Mhm.
There's no better way to do it. Okay.
Okay, I was just wondering.
Okay, no, that's a great question. Great question. I'm going to join Astra's room, and then probably in a couple minutes we'll go back to our group. Hey guys, are we all fighting?
No, we're not. I think we
No?
agreed on, no, I think we agreed on an answer.
You agreed on an answer? You haven't declared war or anything? That's good. Yay, you guys are the future. So, Tevleen, what is the answer?
So for the one to the NaCl question, we agreed it's because salt is ionic and water's polar, so it's able to pull apart the molecule.
That's the most beautiful answer I've heard so far. I love it. I love it. Absolutely. There are a lot of answers like that have to do with sort of derivative concepts like bonds forming and stuff, but like water pulling apart the atoms, that's perfect, right? Because the dipole from a water can form a bond to the monopole of a sodium, right? Or the monopole of a chloride, right? Just flip the water around and it'll bond to the other item, right? And then they do literally, they pull on the atoms, right? So from that perspective, that's not really a fair question. So if you were simply evaporating sodium chloride, right, in a vacuum, and you heated it up and you melted it and evaporated, and it made and for this case, let's say it evaporated into sodium ions and chloride ions, right? We're not evaporating it into atoms, ions, right? Would that be an endothermic or an exothermic process?
It would release heat, so because like there's energy stored in the bonds that get broken, so that would be exothermic then.
Okay, there's a perspective problem there, right? Because there's when the bonds form, the atoms do work on the environment actually, and they give off heat. So it's actually the energy isn't stored in the bonds. The energy is lost in the formation of the bond. Does that make sense?
Oh.
It's like it's like when something gets hot and it gives off heat, then you can say that energy is lost or dissipated.
So
right?
Endothermic because it takes energy to break the bonds and then separate the.
Exactly. Yes, exactly. And whenever you make a bond, you have to dissipate heat. Otherwise, boing, things bounce off, right? It's kind of a weird thing, in physics and chemistry. When you talk about elementary or atoms and molecules, they have to have a way to give up energy in order to form lower energy structures, although they normally do. Okay, you guys are doing great. I'm proud of you. Cool. Okay, I'm going to go back to a different room, and then I'm going to then we will go back to Wait, where's my other breakout rooms here? Leave room, more. Breakout rooms, there we go. Okay. Okay, bye-bye. I think I have not visited Sedans. Oh, no, there we go. Hey guys, how are we?
Good.
Excellent. So what's the answer?
It's because they're both polar molecules, so they can pull each other apart. Because part of the molecule is more electronegative than the other, so they align and can pull each other apart.
Okay, that's good. Max?
Yeah, because like, wait, sorry. Yeah, the sodium. So I'm having a hard time explaining this, but like, I'm
Oh,
pretty
that's
sure
okay.
like the sodium atom is like the cation.
Okay, yeah.
And then the chlorine atom is the anion, and like they're attracted to the negative. They're pulled apart by the respective negative part of the water molecule and the positive
Right,
part of the water molecule.
right. Exactly right. There's, there's a little bit of a semantic question here when you talk about dipoles versus, and one thing we don't ever talk about is monopoles, right? But really ions are monopoles because they are a single polarity of charge, right? And a dipole is a combination of a positive and a negative, right? So, and then you can have quadrupoles and higher poles, whatever. But so sodium chloride is a collection of monopoles, right? Positive and negative, right? And they're attracted together by the, Coulomb forces. Yeah. And water, I mean, this is semantics, right? So your understanding is probably perfect, right? But water, we can think of water as a dipole, right? Because it has, a positive, two positive ends and a negative end, right? And it's very accurate, I think, to think of the water as sort of tearing apart the sodium chloride, yeah? Because the hydrogens can hydrogen bond to the chloride, pull them off, and then the oxygens can hydrogen bond to or dipolar bond to the sodiums and pull them off. So in order for this process to go forward, and ignoring entropy for the moment, which of those two processes would have to be stronger? The monopolar interaction between sodium and chloride, or the monopole dipole interactions between chloride and water and sodium and water?
The second force you just mentioned would have to be stronger, because then like that's how it dissolves.
Exactly right. All right. So what about sodium sulfate? Okay, there's another example. Or ammonium sulfate's a little bit better, right? When you dissolve it in water, it dissolves, but the water gets cold. Right? That's an example of endothermic reaction. And in that endothermic reaction, the heat of formation of the crystal lattice is greater than the heat of solvation of the ions. Right? So it actually takes energy from the system to tear it apart. But it still happens. And the thing that drives that reaction forward is entropy. And this is the work of J. Willard Gibbs around 1900. And he was this Connecticut chemistry professor, and he did all this brilliant work on thermodynamics based on these principles, and he never published it. He was like, "Ah, no, people know this stuff." Ah, and then he finally published it in the Connecticut Academy of Sciences, and nobody has heard of that. And so nobody picked it up for like 20 years. Anyway, I digress. So I'm gonna close the rooms, and I will see you all in the main room. Okay. Hey, everybody. So let's see now. As we went along, we got to better and better explanations of how of this whole process, right? And I think we can all agree. I think we can all kind of get on this page, right, where we can see that as we dissolve sodium chloride, that's an endothermic process, right? From just the perspective right now, no solvent, right? We just expand the nuclei. Sorry, guys. We expand the nuclei. You guys were like ripped from your rooms, right? You were talking. I'm sorry. But you can expand the nuclei, and that's endothermic, right? And then you can pop these solvents into existence, and they'll bind to those expanded nuclei, and that's exothermic, right? And if you add up those two terms, right, those are basically the internal energy of the atoms, right? And that will, in that case, in most cases of dissolving solids, the solvation will be a greater amount of energy gain than you lose by tearing the ionic crystal apart, right? But there are exceptions, right? There's quite a few. And one of them is ammonium sulfate. And if you dissolve ammonium sulfate in water, the water will get cold. And my question for anybody who cares to answer it right now is like, what is going on there? Vigo's on strike. I don't blame you, Vigo.
No, I'm just very mad.
Oh, I'm sorry. I'm sorry.
It's just APs, but you know.
Oh, got it. Ah. Okay. So did scores just come out or something on this? Oh well. I can tell that you're destined for greatness, Vigo. Even if it's like a weird little greatness like mine, where I get to talk to people and enjoy myself. But it could also involve a lot more money in your case, so don't worry.
Well, thank you, Dr. Terrell. I appreciate that. Also, for your question.
Yeah, no. Yeah.
Was it why does water get colder when you dissolve sodium chloride?
Sodium chloride, I'm not sure. I think sodium chloride is probably very neutral energetically. Ammonium sulfate gets cold.
Oh, wouldn't it just be because
it's the same endothermic?
Yeah, therefore with energy.
Yeah, it's endothermic, but like, why does it happen?
Oh,
like
why?
Most things that are spontaneous. Yeah.
Oh.
Yeah.
Should I not answer this or?
Oh, please, by all means, answer, because I think everyone else is on strike.
Oh, okay.
Because
Well,
it's strike. It's the strike hour, right? And Kita, are you on strike?
No, I'm fine.
Okay. All right. So we've got a couple strike breakers here. So this is not holding up. So, but go ahead, Vigo. Go ahead, Vigo.
well, I was just thinking that, so since ammonium sulfate, you would have, it's an ionic compound, so you would have the partial charges at the end because they're ions. So what would happen is that since it's in water, for example, the hydrogen parts of the water would gravitate towards the anion of ammonium sulfate, which I'm assuming is sulfate, and the oxygen parts would gravitate towards the ammonium part. And eventually those forces of the water would become so strong that it would tear the ammonium sulfate apart.
That's a perfect description that doesn't quite work. Because if you add up all those forces, in the case of ammonium sulfate, the crystal forces are actually stronger than the solvating forces. So why does it happen? It's an example, of which there are many in nature, of a process that's spontaneous, but which absorbs heat from the environment. Okay, and I'll tell you what this is really related to. It's an Irish scientist named Murphy. And this Irish scientist has a law, and that law is called Murphy's Law. And Murphy says that what can go wrong will go wrong. But in this case, it's what can happen will happen. Right? Right? And so if this ammonium sulfate in water can dissociate into ions, it will. You know, there's actually an energy equivalent to that, and that's called the entropy. Entropy is a bookkeeping term for the different amount of different ways that stuff can happen, right? And every phase of every molecule has a certain entropy, right? And so in the case of ammonium sulfate, this stuff falls apart, and it does so at the expense of the thermal energy of the bath, right? It doesn't contribute any energy. It takes it up. But in so doing, it makes a mess, right? So it's like your bedroom, you know? It just naturally gets messy. I should say it's like Rohan's bedroom, right? Which has become so dense with energy that it now absorbs even light. And we do not know how Rohan can remain at the event horizon like he does. But he does. Okay, my friends. I love you all. I'm sorry I completely suck as a teacher, but I hope that you're having a decent time. And I will see everybody again tomorrow. Bye.
Thank you.
Bye. Thank you.
Thank you.
Thank you.
Bye. You're welcome. Thank you so much.